So the last topic that I want to talk about today is the topic of what are called bifurcations. And this has to do with any constants that you might see inside the differential equations. So we say that any unspecified constant in a given differential equation is called a parameter. And typically, we can write this as, if we have an autonomous ODE, then the ODE is going to be y prime is equal to f of x, and it depends on the parameters lambda 1 to lambda l. In general, we can have l possible parameters, many possible parameters that the ODE depends on. This is an autonomous ODE. And a non-autonomous ODE are the most general kind. Will just depend on the independent variable as well as t, the f function, as well as all these parameters. And the idea of bifurcation theory and bifurcations is that we want to study, and one of our main approaches is going to be to study how the solution changes with respect to its parameters. And in general, this can be pretty severe. We'll see that what is a stable or asymptotically stable critical point for one value of a parameter could switch at a given point to an unstable critical point, or you could get the appearance of a new critical point. Many possible things could happen. So we'll investigate this through a number of different examples. Specifically, we will start with the exponential ODE and then move on from there. So the exponential ODE, all of these examples will deal with a non-dimensionalized ODE. So in general, the exponential ODE might look like this: y prime equals lambda y, where lambda is a parameter. And without even going through and solving this ODE, we can identify the equilibrium points. These are when the right-hand side of the ODE is equal to 0. So in this case, when lambda times y is equal to 0, and this implies that we always have a critical point when y equals 0. There's always one critical point in this ODE. And lambda is less than 0, this critical point is going to be asymptotically stable. And if we draw our phase line diagram, this is exactly what this shows. This is this critical point at 0, at y equals 0. When lambda is negative and y is less than 0, lambda times y is going to be positive. And when y is greater than 0, lambda times y is going to be negative. And this is why 0 ends up being an asymptotically stable equilibrium point when lambda is negative. If lambda is equal to 0, this picture is going to change slightly. Because lambda equals 0 means that y prime equals 0. So at every point, there's actually no motion of the solution. It just means that y is staying constant at whatever the initial condition is. And lastly, when lambda is greater than 0, when y is less than 0, lambda times y is less than 0. And when y is greater than 0, lambda times y is positive. So any solution with initial condition on this interval right here from negative infinity to 0 is going to go to negative infinity. And any solution where y is positive with an positive initial condition is going to go to positive infinity. So we see that at 0 we have a switching of this equilibrium point from being an asymptotically stable equilibrium point to an unstable equilibrium point. One way of visualizing this is through a nice picture known as a bifurcation diagram. And the general bifurcation diagram essentially is always computed just by drawing out a lambda axis and a y-axis, and then drawing the curve which represents f of y lambda being equal to 0. So for this curve, this corresponds to lambda times y equals 0. Which corresponds to a straight line when y equals 0, and a straight line when lambda equals 0. And our axis, or I should say our region in two-dimensional space, is split into 4 parts, the 4 quadrants. In this quadrant, f of lambda, y lambda is positive. In this quadrant, f of y lambda is negative. In this quadrant, f of y lambda is positive, and in this quadrant, f of y lambda is negative. And if you want, you can visualize the phase lines from before as being any fixed value of lambda So if lambda is negative, then f of y lambda is positive in this region. So on the phase line diagram, or f of y lambda is negative. So on the phase line diagram, you're going to have that solutions travel in this direction. It's positive in this quadrant, so the phase line diagram is going to have solutions traveling in this direction, which means that for any one of these values of lambda where lambda is negative, this is a stable critical point. Y equals 0 is. And likewise, for any points lambda and y that are in this quadrant, that f of y lambda is positive. And for any values in this quadrant, f of y lambda is negative. So we can recapture those all of the phase line diagrams from before with this bifurcation diagram. And this is showing very clearly that at lambda equals 0, there's a switch. And on the phase line diagram, the switch is typically denoted using a dotted line when we have an unstable critical value, or equilibrium value for y prime. So this is very neat and is very, very connected in a certain way to multivariable calculus, calculus 4. We can directly see this. So this is called a bifurcation diagram. And if we go through and plot this out, you can use Desmos and or GeoGebra to get a very nice plot and visualization. In this plot here that I'm showing, we have this bifurcation diagram for this example. And you see that as we change the value of lambda, where I'm using a here for the lambda, as we move, give an equilibrium point always at y equals 0. This is the y-axis and the lambda axis right here. And then as we switch from negative values of lambda to positive values of lambda, that equilibrium point goes from being stable to unstable. And the connection to multivariable calculus comes from if we make a lambda axis and x-axis and we graph out that f function. So we consider the three-dimensional graph of the f function. So this is the lambda axis right here. This is the y-axis right here. And we see that this f function is positive in this quadrant, it's negative in this quadrant. It's right here. It's positive in this quadrant and it's negative in this quadrant. So this picture exactly explains this bifurcation diagram, that at lambda equals 0 you have a bifurcation in this point where it switches from being a stable critical point, asymptotically stable actually, to an unstable critical point because of the behavior of the f function. This is a graph of that f function. So let's see this in another example. See that this is a relatively simple example, and by the way, this does correspond exactly to the solution. When you solve this ODE right here, the solution ends up being, as we've seen, absolute value of y is equal to absolute value of y naught times e to the lambda t. And you can clearly see that when lambda is negative, you're going to have a stable, 0 is a stable value or a stable equilibrium point, and when lambda is positive, it's an unstable equilibrium point. But we don't need the actual solution to go through and do this analysis, and this is one of the big ideas of using bifurcation diagrams, is that you don't necessarily need the exact explicit solution to analyze the qualitative behavior of your solution. So the next example we'll consider is a stereotypical example of what's called a saddle node bifurcation. And this is going to be for the ODE. Y prime is equal to lambda plus y squared. And there are many types of functions that exhibit saddle node bifurcations, but this is a great example. This is going to have equilibrium points when a plus y squared is equal to 0. And this, just like before, can be split up into separate parts or separate procedures for various values of a. When a is less than 0 or negative, this expression becomes negative absolute value of a plus y squared is equal to 0. And this equation has two solutions. Y is equal to positive the square root of the absolute value of a, and y is equal to negative square root of the absolute value of a. So there are two equilibrium points when a is negative, or when lambda is negative, sorry, not a. when lambda is 0, we have the equation y squared equals 0, which only has one solution. This is the solution y is equal to 0. So there's one equilibrium point. And then lastly, when lambda is positive, you're going to have to solve the equation absolute value of lambda, which is positive, plus y squared is equal to 0, which has no real solutions. So there are 0 equilibrium points for this value of lambda. What does this mean about the phase line diagram? This is telling us that when lambda is less than 0 and lambda is negative, we'll put a mark here at 0. And I'll make a copy of this. We're going to have to consider the other cases as well. But when lambda is negative, we have two critical values, or two equilibrium values. One at negative square root of the absolute value of lambda, and one at positive square root of the absolute value of lambda. And the solution in each one of these regions, if you look at the sign of this function, or the sign of lambda plus y squared, when y is less than negative lambda, or less than negative square root of lambda, this value right here is going to be positive. When y is between negative square root of lambda and positive square root of lambda, lambda plus y squared is going to be negative. So y will be decreasing. And when y is greater than the positive square root of lambda, lambda plus y squared is again going to be positive. So solutions are going to travel in this direction because the f function is positive. In the case of lambda equals 0, we have one critical point, one equilibrium point where y equals 0. In this region, y squared is positive, and in this region, y squared is also positive. So in both regions, the solution is increasing, which means that at lambda equals 0, we have a new critical value, 0, which is an unstable critical value. So we get a switch at lambda equals 0 from having two critical values, one stable, one unstable, to a critical value one critical value that's unstable. And then when lambda is positive, you have no critical values. and lambda plus y squared is always positive. So we're just a constant increasing for any initial condition. Just like before, we can take a look at this, the bifurcation diagram of this. And the bifurcation diagram looks a little bit different. We have our lambda axis and our y-axis, and we consider what the curve lambda plus y squared equals 0 looks like. Oh, this is just the curve lambda equals negative y squared, which is a parabola. And for all points lambda y to the right of the parabola, f of y lambda is positive, and for all points to the left of this parabola, f of y lambda is negative. And this is very clearly showing the behavior that we found before. Is that if f of y lambda is positive here, the direction of y for any initial condition on this, for this fixed value of lambda, is positive. It's negative here, and it's positive here. So we have a stable critical value here and an unstable critical value here. Then for lambda equals 0, so the rate of change is positive here, y prime is positive here, and it's positive here. So when lambda equals 0, we have an unstable critical value here. And then lastly, for any positive lambda, there are no critical values or equilibrium values of this ODE. So according to our previous convention, we need to make this a dashed curve, because any critical value on this curve is an unstable critical value. And this is the correct bifurcation diagram for this example. So if we take a look at this, we'll look at the bifurcation diagram first in Desmos, just like before. You can clearly see that we have two equilibrium values, one stable, one not stable, for any fixed value of lambda, up to when the moment when a equals 0, where we have that the nature of the solution's changed, and we have one critical value, which is an unstable critical value. And then for positive values of lambda, there's actually no critical values. So this bifurcation diagram is telling us a lot. And just like before, we can get some more insight into this by looking at the three-dimensional plot of this f function. So if we plot the function lambda plus y squared, where this red axis is the lambda axis, this green axis is the y-axis, just like before. In the surface here is the surface plot of the function z is equal to lambda plus y squared. Right, we're seeing exactly this bifurcation curve that we obtained before, and we gain a little bit more insight into what's going on here in terms of our parameter space. So in this region, right here, this gray region, this is negative, this function is negative, and outside of this parabola, the function is positive, which exactly explains from before what's going on, why we have all of these points are stable critical points, all of these points are unstable, and once we pass 0, we have no critical points, no critical values of this function. So as you have already seen in this example, hopefully, you can see that we can have some pretty severe changes in the nature of solutions for even a relatively simple ODE. And you can go through and exactly solve this ODE as well. This is a separable ODE. It's a little bit more difficult to solve, but it's not too bad. You're going to have either the arctangent function or the hyperbolic tangent function involved when you go through and integrate this separable ODE. But if you were to do that, the solutions are going to exactly correspond to what we're observing here, but we haven't even gone through and solved the ODE, which is very interesting. This is showing that we can use the ODE to qualitatively determine how the solutions are going to behave without even going through and solving it. So the next type of bifurcation that we'll consider is called a transcritical bifurcation. And the example that we're going to use for this is when y prime is equal to lambda y minus y squared. And so this has equilibrium points when the function lambda minus y times y is equal to 0. Which means that we'll always have two equilibrium values. One where y equals 0 and one where y equals lambda. So for any case, this is going to be, I guess I should say we have two equilibrium values, two equilibrium points. This is for lambda non-zero. When lambda is equal to 0, this equation reduces to the equation negative y squared equals 0, which has the solution y equals 0. So we have one equilibrium point in this scenario, where lambda equals 0. So looking at the phase line diagrams, when lambda is less than 0, 0 here. And I'll make a copy of this because we're going to repeat this picture 2 more times, just like before. Lambda is less than 0. We have a critical value at 0. And we have a critical value at y equals lambda. And if y is less than lambda, lambda minus y times y is going to be negative. So any solution starting in this orbit will be have a negative slope, or negative rate of change. For any solution in this region, from lambda to 0, lambda minus y times y is going to be positive. And for any solution in this region right here, lambda minus y times y is going to be negative. So this corresponds, this is exactly the correct baseline diagram. At lambda equals 0, we have 1 critical value, so we're switching from 2 critical values to 1 critical value. And our differential equation is y prime equals negative y squared, which is always going to be negative. And this is true up here as well. So for negative values of lambda, 0 is an asymptotically stable critical value. For positive values of lambda, or for lambda equals 0, 0 switches and becomes an unstable critical value, and we also lose a second equilibrium point. And then lastly, when lambda is positive, we go back to having 2 critical values. 1 when y equals 0 and 1 when y equals lambda. And the nature of the critical values switches again. 0 is still an unstable critical value. Lambda minus y times y is less than 0. But in this region now, lambda minus y times y is positive. So 0 remains an unstable equilibrium value. And at y equals lambda, so when y is above this, lambda minus y times y is negative. So we get this switch where 0 becomes an unstable equilibrium point. It's initially a stable equilibrium point, and when lambda switches from negative to positive, it becomes an unstable equilibrium point, and we get this new equilibrium point, y equals lambda, which is now a stable equilibrium point. So to visualize what's going on here, just like before, we can draw the bifurcation diagram. And on this bifurcation diagram, we're going to have two curves. The first one is going to be the curve at y equals 0. And the second curve is going to be the curve y equals lambda. And this is where things become a little bit more clear, because we can see that this function f of lambda, or f of y lambda, is going to be negative in this region. It's going to be positive in this region. It's going to be negative in this region right here. And it's going to be positive in this region right here. So if you fix the value of lambda and you look at the corresponding phase line in any one of these regions, the picture that you'll get, well, if f of y lambda is negative in this region, that means that the solution is going to decrease. If it's positive in this region, then it's going to increase here. And if it's negative in this entire region down here, then it's going to decrease. And then same thing right here. And then when lambda equals 0, you can do a phase line at lambda equals 0. It's going to be decreasing right here, and also decreasing right here. So we have this, what's called a transcritical bifurcation, and our bifurcation diagram, well, any point here is going to be unstable. It represents an unstable equilibrium value. So we have to draw a dashed line. And furthermore, any critical value right here is going to be unstable. So we see that a transcritical bifurcation is when we have this switching from an unstable equilibrium point and a stable equilibrium point, and the meaning of each switches as the parameter passes through a certain point. So again, if we open up our plot, this is shown in Desmos here, where as I take lambda and have it cross here, when lambda goes through 0, right, we switch from having an unstable equilibrium point and a stable equilibrium point to also having an unstable equilibrium point and a stable equilibrium point, but the meaning of these two points switches. So 0 becomes unstable, and y equals lambda becomes a stable critical value. This is perhaps best seen when we open up a 3D plot and you see exactly the plot of the function z equals lambda minus y times y, where again this is the lambda axis right here and this is the y-axis right here. You see very clearly that in these two regions the function f is positive, and in these two regions the function f is negative. So this is a very, very nice geometric approach using multivariable calculus to understand what's going on with these bifurcations in our solutions. And really the number of types of bifurcations that you can see are only limited by the type of functions that you can imagine. So there are many different types of bifurcations that can occur. I'm just giving you some examples of some common ones that are talked about and that are considered. Mainly because they appear very commonly in applications. So the next example is known as a pitchfork bifurcation. And the example that I'm going to use for the ODE here is going to be y prime is equal to y minus 1 times a minus 1 minus y minus 1 squared. And this has equilibrium points when y equals 1. Y equals 1 is always an equilibrium point because this always makes this equal to 0. And when a minus 1 minus y minus 1 squared is equal to 0. And we want to I'll use lambda here to be consistent with my other notes. And this equation only has solutions when lambda minus 1 is positive, or when lambda is greater than 1, greater than or equal to 1. And the solutions that it has are given directly by y is equal to 1 plus or minus the square root of a minus 1. Just solving this quadratic for y in terms of lambda. So what we're seeing here is that if lambda is less than 1, we have one critical value, and the phase line looks like this. So this is y equals 0, y equals 1. So we have one critical value at y equals 1. And if you take y less than 1, this function is going to be positive. And if you take y greater than 1, the function f is going to be negative. So this is what the phase line looks like for lambda negative. On the other hand, when y is positive, we're going to have a slightly different picture, and when y equals 0, we're going to have a slightly different picture. No matter what, y equals 1 always remains a critical value. But if lambda is 0, we'll see that we still have one critical value. Sorry, yes, if lambda equals 1, not 0, we'll still have one critical value. And this expression will be negative y minus 1 squared, which is going to be negative times y minus 1. So this will still be positive when y is less than 1, because you get negative times negative, which is positive. And then when y is greater than 1, it will be negative. So even at lambda equals 0, this 1 remains an asymptotically stable equilibrium value. But the interesting thing about the pitchfork bifurcation is that when now lambda is positive, we go from having one stable critical value to having 3 critical values. One critical value at, call it, I'll call these two roots y1 and y2. The negative root being y1 and the positive one being y2. So you go from having one critical value, one stable critical value, to having 3 critical values. And if you look at the value of f in each one of these regions, f is positive to the left of y1. It'll be negative to the right of y1, but less than 1. It'll be positive to the right of 1 and to the left of y2. And it'll be negative to the right of y2. So the pitchfork bifurcation is when we go from having one critical value to having 3 critical values. In the stability of these is changing. Right? One's going from being an asymptotically stable critical value to being an unstable critical value. And these two new critical values that pop up, y1 and y2, are both asymptotically stable. So these are what the phase line diagrams look like for this bifurcation problem. And we can go through and really see what's going on here and why this is called a pitchfork bifurcation when we look at the bifurcation diagram. So we always have a critical value here at y equals 1. Oops, sorry, and I wrote lambda equals 0 here, but I should have wrote lambda equals 1. I apologize for that, just a typo on my part. So here at lambda equals 1, we have the appearance of 2 new critical values for any value of lambda greater than 1. And if you plot out these curves right here, the curve y equals plus and minus the square root of lambda minus 1, this is just going to be a quadratic opening, or parabola opening, like this, and a parabola opening like this. Oh, and I should do those in bold so we really see this curve. And this is why the pitchfork, or how the pitchfork bifurcation gets its name. Because this looks like exactly like a pitchfork or a trident. And in this region up here, f of y lambda is going to be negative. In this region down here, f of y lambda is going to be positive. And what we're seeing is that across this region right here, f of y lambda goes from being positive to being negative. So for any fixed value of lambda less than 1, you're going to recover exactly the phase line diagram that we talked about before, where f of y lambda is negative here, so the function is decreasing, and f of y lambda is positive here, so the function is increasing. And this holds all the way up to and including the point y lambda equals 1. But then when lambda is greater than 1, you get a switch. Alright, this is still negative in this region, but it's positive in this region right here. It's negative in this region right here. And it's positive in this region right here. So following the convention that we introduced before, this now becomes a dotted line, or dashed line, because this line is representing an unstable critical value or equilibrium point of our differential equation. So the pitchfork bifurcation is very interesting because of the fact that you have one critical value, an asymptotically stable critical value that switches into an unstable critical value, and you have the appearance of two new critical values to your differential equation. So just like before, we can take a look at this using Desmos and GeoGebra to kind of shed some light on what's going on, get a better visualization of what's going on. In Desmos, we're seeing exactly what I just drew as we cross 1 right here, the point lambda equals 1. You have the appearance of two new critical values, and the type of critical value for y equals 1 changes. It goes from being asymptotically stable to unstable, along with two new stable equilibrium points that appear. And if we look at a plot of this, this is exactly what we see. So this blue surface right here is the function z equals f of y lambda, and you see that this is why all of these points are stable, asymptotically stable, because it's the function's positive in this region and it's negative in this region right here. But at the point lambda equals 1, this is the lambda axis and the y-axis, when lambda equals 1, this function switches its behavior, but you get this region here where the function goes from being positive to positive, and then back to negative. And this explains why at this critical value, or at this point 1, you get a change in the characteristic behavior of solutions. I think it very clearly explains why this happens. So all of these are common bifurcations that we actually see in applications, various applications. And the next example is probably one of the most complicated out of all the examples we're going to look at, but it's also very common to see in real-world models. And this is the example of what's known as hysteresis. And to show what hysteresis means, we'll look at the example y prime is equal to lambda plus y minus y cubed. Oh, and let me turn on the notes right here. So hysteresis is a very common phenomena that we see in many different applications, but it's quite a complicated phenomena. We'll use this example to illustrate exactly what we mean by hysteresis. So just like before, we know that this is going to have equilibrium points when lambda plus y minus y cubed equals 0, which is a general cubic equation, or cubic polynomial equation. You can rewrite this if you want as when lambda is equal to y cubed minus y. And there is a cubic equation that we can use to solve exactly for y in terms of lambda, but it's a little bit complicated to use, so I'm not going to use it here. I'm just going to note that for special values of lambda, we can solve this exactly, very nicely. So if you want to go through and use the cubic equation here, you're welcome to do so. However, it's going to get a little bit complicated. So we'll just look at when lambda equals negative 2 over 3 square root of 3. We have two special solutions. And this is going to be directly verified. Solutions are going to be y. And I'm going to number these specifically. We'll say y3 is equal to 1 over the square root of 3. And y1 is equal to negative 2 over the square root of 3. And when lambda is equal to 2 over the square root over 3 times the square root of 3, we have two other solutions. Y2 is equal to negative 1 over the square root of 3, and y4 is equal to 2 over the square root of 3. So the phase line diagram for this example has to be split into all these possible values of A. Or of lambda. So when lambda is less than negative 2 over the square root of 3 times 3, and we'll put 0 here, and we'll put a spot for y1, a spot for y2, a spot for y3, and a spot for y4 on this diagram right here. So when lambda is less than negative 2 over 3 times the square root of 3, there's only going to be one root to this, or one real root, I should say, to this quadratic or cubic polynomial. Call that YR1. And when this is the case, if we have one equilibrium value, you can use the cubic formula to calculate this equilibrium value. There will be two other roots to this cubic polynomial, but they'll both be complex, so not real values. So for values of y less than yr1, this function is going to be negative, and for all values of y greater than r1, this function is going to be positive for all values less than r1 and negative for all values greater than yr1. So the root of this polynomial when lambda is less than y1 is going to be an asymptotically stable equilibrium value. And we're going to have to make multiple copies of this without these values here. So let me just erase these values for the arrowheads here. and we'll copy this picture. We're going to have to copy the picture a couple different times. One, two, three, and one more. So when lambda is equal to negative 2 over 3 square root of 3, we've seen that we have two solutions, y1 and y3, so two equilibrium values. And if y is less than y1, f of y comma lambda is positive. When y is greater than y1 but less than y3, it's negative. And when y is greater than y3, it's also going to be negative. And you plug into this function right here. So we're going from having one stable equilibrium value to now having two equilibrium values, one being stable and the other being unstable. When lambda is between negative 2 over 3 root 3 and positive 2 over 3 root 3. We'll actually have three real roots to this equation. You can go through and use the cubic formula to show this. That when lambda is between these two values, this equation has three real roots, and the real roots are going to generally be greater than y1, less than y2, one root that's going to be greater than y2 and less than y3, and one root that's going to be greater than y3 and less than y4. So you can call this yc1, yc2, and yc3. This is for any value of lambda in between these two values. You can show this using the cubic equation. And the idea, though, is that when y is less than yc1, you have that the f function is positive. When y is between yc1 and yc2, you have that it's going to be negative or decreasing. When f is between yc2 and yc3, you have that it's going to be positive. And when y is greater than yc3, it will again be negative. And this is the case until lambda reaches positive 2 over 3 root 3. In which case, as we saw before, and it's easy to go through and check this, when lambda equals 2 over 3 root 3, we have two roots, y2 and y4. So we'll have two critical points, two equilibrium points, where when we're less than y2, the solution is increasing. When we're greater than y2, the solution is also increasing. And for initial conditions greater than y3, the solution is decreasing. Oh, no, not y3 here. Sorry, y4. I highlighted the wrong value. So y2 is an unstable critical point, or equilibrium point, and y4 becomes an asymptotically stable equilibrium point. And then the last situation here is when lambda is greater than 2 over 3 root 3. In which case, we'll have one root, call it yr2, and for any value of y less than yr2, y prime is going to be positive. And for any value of y greater than yr2, the y prime value is going to be negative. So we have, back to the initial case we started with, we have one equilibrium point which is asymptotically stable. So this is by far the most complicated of the examples that we've seen of bifurcation so far. It's going to pay to look at the bifurcation diagram and dissect it. To see what insight it provides us into this hysteresis phenomena. And if we immediately go and we plot out what this is going to look like, the curve that we're plotting is the level curve a plus y minus y cubed is equal to 0, which corresponds to a cubic curve, which opens, we're going to do lambda, not a. So it's a cubic curve opening along the lambda axis, and it looks like this. I can do it a little bit better. This is what our curve looks like. And we can see that immediately this phenomena is directly explained based on this level curve, because in this region, the region to the left of this level curve, the function is going to be negative, and to the right of this level curve, the function is going to be positive. And we see very clearly what was found before, if we draw out some sample fixed values of lambda to investigate this. By the way, those special values for lambda are right here, correspond to this point right here, and correspond to this point right here. So this is negative 2 over 3 root 3, and this is positive 2 over 3 root 3. So when lambda is less than negative 2 over 3 root 3, you have one stable critical value. The function's decreasing here, and it's increasing here, because in this region f is positive, and in this region f is negative. It's positive here and negative here. At the switching point, negative 2 over 3 root 3, we have the appearance of a new critical value. The function's still negative here. And it's negative here. And it's positive here. So these 2 points correspond to our critical points. We have 2 critical points for lambda equals negative 2 over 3 root 3. When lambda switches to be between negative 2 over 3 root 3 and positive 2 over 3 root 3, we have a switch where function's still negative here, but it's positive here, and it's a negative here, and it's positive here. So you have a switch where you have now 3 critical points for the differential equation, and the stability of the outer 2 critical values is that they're asymptotically stable, and our inner point becomes, well, it's unstable here and it's unstable here. This corresponds to 2 critical values, whereas when lambda is between these 2 numbers, you have now 3 critical values. And that holds all the way up until we get to lambda equals positive 2 over 3 root 3. Where you have that f is negative here, it's positive here, and it's still positive here. So this is an unstable critical point, which is exactly what we saw before, and this is a stable critical value. And the last case is for positive lambda, where we're back to having 1 critical value that's asymptotically stable. So by the convention that we introduced before, that means that this section of our curve, the middle section of our curve, is completely unstable. So we'll draw this as a dashed line. Or dash curve. Because it's representing critical points that are unstable. And this is what a bifurcation diagram looks like for hysteresis. So just like before, if we go take a look at this in Desmos and GeoGebra, so using those two tools, you see that this is exactly a plot of this curve. As we move our value of lambda, eventually we get to this point right here, which is where one stable critical value turns into two stable critical values, or two critical values. One is stable and one is unstable. And this then now switches into having three critical values, one stable, one unstable, and the third one stable. And then as we increase up to this point, we have two critical values again, one stable, one unstable. And then for lambda positive, we have that solutions are characterized by just one critical value. And on our 3D plot of this, it's very, very well explained. If we plot the surface plot of this function, the function z equals lambda plus y minus y cubed. You see that in this region right here, this is the lambda axis again, this is the y axis, and plotting this function gives you a curve or a surface plot where in this region the function's negative, in this region the function's positive, and it directly explains the behavior that we're seeing here. But we've done all of these examples without actually going through and solving the underlying differential equation. That's kind of the point of this bifurcation analysis, is to go through and be able to understand how the solution to a given differential equation is going to behave without going through the process of solving the differential equation. And we'll see that the analogs that we'll develop for systems are going to be very, very powerful. So using GeoGebra and Desmos, we can go through and get a very nice picture of what's going on here. So for negative value, or for values of lambda less than negative 2 over the square root of 3, you see there's one critical point, or one equilibrium point of our differential equation. And then at the value lambda equals negative 2 over this 3 times the square root of 3, you get that one critical value turns into, we have two critical values. One is stable, one is unstable. And then when lambda is between negative 2 over 3 root 3 and positive 2 over 3 root 3, you have the appearance of three critical values of our function, and you have a loss of stability in the middle one. The middle one is unstable. The other two are stable, and that happens all the way up and until lambda equals positive 2 over 3 root 3, in which case you have two critical values again, so we go from 3 to 2. One is stable, one is unstable. And then for values of lambda that are greater than 2 over 3 root 3, you have, again, one critical value, which is a stable critical value. So this is probably best seen when we visualize this as a surface plot. And you see here, the x-axis is this red axis, or the lambda axis is this red axis, the y-axis is this green axis, and this is a surface plot of the function z equals lambda plus y minus y cubed. So you see exactly what we said before, that this function is positive in this region, it's negative in this region, and this level curve is separating these two regions from one another. And this exactly explains, as we talked about before, the qualitative behavior of the solutions to this ODE. And what's amazing for all of these examples is that we haven't gone through and solved a single ODE. We went through and just using the differential equation itself and a little bit of knowledge of multivariable calculus, been able to classify the critical points and the behavior of solutions to the ODE for the entire range of its parameter space, for the entire range of its parameters. So the last example I'll look at is the logistic equation, and this is going to be the non-dimensionalized form of the logistic equation. Y prime is equal to lambda 1 times y times 1 minus y over lambda 1. And we can split this into multiple different parts after we solve for the equilibrium points. Equilibrium points occur when not lambda 1 here, sorry, lambda 2. Either y equals 0 or y equals lambda 2. So this means that our phase line diagrams are going to be a little bit more complicated. We have to go through and look at multiple scenarios. And what makes this slightly complicated is that we have two parameters now. So we have to look at when lambda 1 is negative and when lambda 2 is negative. We have to look at when lambda 1 is equal to 0 and lambda 2 is negative. You have to look at when lambda 1 is equal to 0 and lambda 2 is positive. And lastly, we have to look at when lambda 1 is positive and lambda 2 is negative. And when lambda 1 is positive and lambda 2 is positive. Oh, and I'm forgetting one. We also need to look at when lambda 1 is negative and lambda 2 is positive. So in any case, we're always going to have that y equals 0 is a critical value. Then when lambda 2 is negative, that means that y equals lambda 2 is a critical point. When lambda 2 is positive, that means that y equals lambda 2 is a critical value. we have the same picture here. And then the same thing here. And this is lambda 1 equals positive and lambda 2 is negative. This is when lambda 1 is positive and lambda 2 is positive. So when lambda 1 is equal to 0, this is it for the phase diagram, because if lambda 1 equals 0, y prime equals 0. So we really have no change, which means there's going to be no arrows on the phase line diagrams for these two cases. However, for lambda 1 negative and lambda 1 positive, the phase line diagrams are going to be switching up and changing depending on the various values of lambda 2. So visualizing this, in the phase space is going to involve a function of 3 variables, not just 2 variables. So lambda 1, lambda 2, and y. So it's a little bit more complicated to do a bifurcation diagram and to visualize this like we visualized it before. But trust me, it's definitely possible, and you can do it for a function of 3 variables. If you go to any higher degree function where you have more parameters, it's not super easy, which is why the phase lines are probably the best way of visualizing the behavior of this function. But you see, if we kind of take a look at this for a couple of these different values, so our general solution is going to take this form where r is our lambda, and this will conclude today's lecture. Thank you so much for tuning in, and I hope you have a great day.